Okay, so now we're going to prove the theorem that I mentioned last time, which describes a presentation for an edge group in terms of this other group. So it's a group isomorphism like this. So let me remind you of the setup. So here, K is a simplicial complex. And let's say the vertices are V0 up to Vn, and let's say P is V0 is the base point. And let's fix T in K a maximal tree. So I called this L last time, but let's call it T now. And we define a group GKT, which has generators Gij whenever Vi, Vj is a simplex of K, and relations so there are two kind of relations. Gij is 1 if Vi, Vj is in the maximal tree, and Gij, Gjk is Gik if Vi, Vj, and Vk, these are span a simplex of K. So a remark is that this maybe looks like what I defined last time, but it's different. So this group, so this GKT is, well, has more generators and relations than last time. But it defines the same group, which I'll leave for you as an exercise. Let me just explain why there are more generators and relations. So here, so I think last time what I wrote was something like here I is less than J, and same thing here, I less than J, and here I less than J less than K. But for today, it's going to be more convenient to ignore these restrictions and define the group in this way. So here we have generators Gij, but also Gji, but also Gii. So in particular, if I is J, then this is just a one element set, and that is in K. That's just a vertex. And so this gives us a generator as well. And right, so we know, right, so we have more generators, but we also have more relations. So for example, we know Gii is just trivial because, well, every vertex is in T. So that follows from this relation here. And then we also know that Gij, Gji is equal to Gii, which is by this second thing, since if there are only 3 indices, this is just an edge. Oh, right, and it's an edge in K. And then this is equal to 1 because of this. So this is saying that Ji is Gij inverse, since their product is 1. And so, okay, so this is kind of illustrating why, despite the fact that there are more generators, we're not actually defining a different group. I mean, in fact, these are mostly redundant. You actually only need Gij for I less than j. But as we'll see, it's convenient to, we'll see why it's convenient to have this slightly larger description for this group G. Okay, so the main thing I want to do is to prove this theorem that GKT is isomorphic to EKP, the edge group. So let me remind you how the edge group was defined. So EKP, this is edge paths that start and end at P. So, P is V naught. So let me write it like V naught, VI1 up to VI N, V naught, up to equivalence which allows us to do moves like reduce any repeated vertex with just a single vertex. If we backtrack like this, then we can just replace that with a single vertex. And then if we have UVW, we can shorten this to UW if we have a triangle UVW, which is filled in like this. So if this is in K. Okay, so now let's start the proof. So let me just say that there's really nothing tricky here. So the proof is formal and algebraic. I mean, which I guess you would expect or guess, because these two groups that we've defined are defined in purely algebraic or combinatorial way. So the proof is going to be similarly algebraic or combinatorial, but I guess mostly algebra, I would say. So what we'll do is we'll define homomorphisms between these two. Let's call them phi and psi. And show that the compositions phi compose psi and psi compose phi are both the identity, the appropriate identity maps. Okay, so this is how we're going to do this. It's going to be hopefully straightforward. So now let's first define the maps. So let's define phi. So this is supposed to go from the edge group to this other group. And okay, so what is this? What do we have to do? We have to say what we do to, so we start with an edge path. like this, and we're supposed to send this to a product of these generators, Gij. But that's not so bad because the Gijs, remember, correspond to edges, and every pair of adjacent vertices gives us an edge, or possibly a vertex that's repeated twice. So this is what we'll send this to. No, Gi1, I2 up to Gin0. So each of these is generators. So note that it's possible that inside of this word you see something repeated twice, in which case here you see an index GII. So this is why we made our generating set slightly larger to include these things. Okay, so this is the map phi, and so note that phi is a group homomorphism because, well, what are the operations here? So here the operation in E is just concatenation. And then here, well, yeah, so you see that if you just concatenate two loops, then you just multiply the two things that you send it to. So this is easy to see. So now let's define the other map, psi, from G to E. And so the way we're going to do this, we're going to define phi by defining it on generators. So remember, this group G is given in terms of generators and relations. So if you want to define a homomorphism on a group that's given in terms of a presentation, you just need to say where each generator goes. And then to check that it's a homomorphism, you need to check that each relation goes to the identity element. So on generators, what we'll do, so we have Gij, and we need to say where we send this to. So before we do that, we need to we need a little bit of setup. So for each vertex Vi and V, let's define, let's choose edge path A to I from V0 to Vi contained in T. So the picture, well, okay. So let me give the full definition of psi and then I'll draw a picture. So then we define psi of Gij to be eta I this is supposed to be an edge path. So then Vi, then Vj, and then eta j reverse. So here I guess I should also say denote eta I bar the reverse path from Vi to V0. And I also want to say we also choose eta 0, which is a path from V0 to V0 to just be V0, constant path. Okay, so let me draw a picture. So we have some VI and VJ, and they're connected by an edge. If we're talking about psi of Gij, there's a generator for each edge. So we have VI and VJ, which are connected by an edge. And here's V0, and what we've chosen for each is a path. Here's eta I. It's contained in T, and then some other path, eta J, from V0 to VT, or to VJ, VI and VJ respectively. And this red piece is contained in the maximal tree. So that it's a tree and it's maximal, which means that any two vertices are connected by a path in this tree. And so we just choose some path. And the, right, so let me just write this definition down again. So psi Gij is this concatenation. So we first do eta I, this edge path, and then we do Vi, Vj, that edge, and then we go backwards along eta J. And you see that this gives you a loop. This is an edge loop based at, this is an edge loop based at P. So thus it's an element in here, which is exactly what we want. Okay, so there is something to check. So to show psi is a homomorphism, we need to show that, let me say it this way, psi sends relations in G, K, T to relations in E, KP. Right, so this is what it means to be a group homomorphism. A group homomorphism is a map of groups that sends relations in the domain to relations in the codomain. So let's just check. There's two kinds of relations. So first of all, so the first case is if Vi, Vj is in T, then we have a relation Gij is 1. And so we had better have that psi of Gij is also 1. So let's compute. So psi of Gij, by definition, this is eta I, Vi, Vj, eta J reverse. But notice that this is a path in T, and T is a tree. So, and it's a loop. So this is a loop. This is an edge loop in T. But T is a tree implies that there doesn't exist, well, this loop backtracks. And so you can simplify it. I mean, if you have some tree and some loop that starts at some point and then ends also at that point, then well, there's not much that it can do. It can go all over, but then since we're in a tree, it has to eventually retrace its steps somehow. And this backtracking allows you to inductively reduce the complexity of this edge loop until you just get to a constant. And so maybe I won't write down the complete details, but then what you deduce from this is that this concatenation is equivalent to It's just V naught. Okay, so this implies that psi of Gij is the identity element. Or sorry, I'm low on space here, but let me write it anyway. So it's psi of Gij is the equivalence class of the constant loop, the constant edge loop, just based at V naught, which is the base point. Okay, so that's the first little bit. The second bit is we have these other relations. So if we have Vi, Vj, and Vk, vertices that span a simplex in K. So we want psi of Gij, Gj, K to be equal to psi of Gik. So let's just check this. So psi of Gij, Gjk is equal to, so by definition, right, so by definition, we're defining this to be this product, because we're defining it on generators. So we're sort of forcing it to be a homomorphism in that way, but we just have to check these relations hold. So psi of Gij is eta I, Vi, Vj, eta J bar, and then psi of Gjk is eta J, Vj, Vk, eta K bar. And now what you see is that this is equivalent. So we have an eta bar eta here, and these cancel. And then we also have a Vj, a repetition, which cancels. So this is equivalent to eta I, Vi, Vj, Vk, eta K bar. And now it's come time to use the assumption here that this triple spans a simplex, which means that this is equivalent to eta I, Vi, Vk, eta K bar. Okay, and then that's exactly equal to psi of Gik. Okay, so good. So this shows psi is a homomorphism. Right, so now we want to show, next is to show that phi and psi are inverses. So let's just look at the two compositions. So first we have this composition. Where we first do, so G to E was psi, and then we do phi. So phi of psi, let's just see what happens when we feed in a generator. It's enough to see that this is the identity. So this is phi of this edge loop that we just constructed, eta I, Vi, Vj, eta J bar. And then now what does phi do to this? Yeah. Well, right. So how did I write this in my notes? Excellent. So my notes just say this is Gij. But the point is, right. Yeah, okay. So let me explain this. Right, so we have this, yeah, right. So this isn't hard to see. So we have Vi and Vj, and as before, we have whatever these paths are, A to I and A to J. Maybe for now I'll draw them. I mean, they might look like this, A to I, A to J, and here's the edge between them. Right. The point is that these A to I, A to J's, these are paths in T. And so after we apply phi, so you know, there's some sequence of edges that we meet along here. And so what phi does is just send, you know, you just write down the generators corresponding to each edge. But the thing is that each of these edges in A to I and A to J are in T, and we have this relation in the G group that says that any generator coming from an edge in T is trivial. So all of these, this bit of the path is going to vanish when we take phi, and we're just going to be left with the generator corresponding to the edge between Vi and Vj, which is Gij. Okay, so that's the explanation there. There's not a whole lot going on. So now let's do the other composition. So E Kp to G Kt to E Kp. So first we do phi and then we do psi. So it's psi of phi of, so now we're supposed to input an edge path, V0, Vi1 up to Vin, V0, an edge loop. So first, phi, we know what this does. It's G0 I1, Gi1 I2, so on up to Gin0. And then psi sends this to, okay, it's a big product now. So we have eta naught V naught V I1, eta I1 bar. Let me write the first two terms, or the first two, and then, so then we have eta I1, Vi1, Vi2, eta I2 bar, and then so on up to the last term is eta In, Vin, V naught, eta naught bar. Okay, we're hoping that this is going to be equivalent to just this edge path that we started with. And well, what you see is that here there's cancellation. So you have these, which will completely cancel each other. And then you have these, which are in repetition. And so this little bit simplifies to, oh, and you should also remember this is V naught. Since eta naught, that's how we chose eta naught. So then there's this repetition. So this little bit here simplifies to like V naught, Vi1, these cancel, and then that's a repetition, Vi2, or let me just, Vi2, and then you have the eta bit. So maybe I'll say just this first little bit here simplifies to this, which is what we're the beginning part of what we're aiming for. And so in the same way, as we continue, then we get all these cancellations, we apply all the relations, and we see that this is exactly, this is equivalent to V naught, Vi1, Vin, V0. Okay, so I'm not writing all the details, but this is how the argument works. And then that's it. So that's the proof. Okay, maybe I want to do one more example. Computing these edge groups. So let's take this simplicial complex. So here are the vertices. This is a triangulation of the projective plane. Let me clean this up. So let's see, do that, and then that, and then that, and that gives you a triangulation. So here's K, and the geometric realization is topologically equivalent to RP2. I think we saw this example before. So, well, okay, so yeah, I'm not going to do this. I'm going to leave it for you as an exercise. Maybe I'll put it on the homework. So compute GKT and see that it agrees with what the answer should be. So we know, oh, no, we don't know. Yeah, I guess we didn't compute this already. So this is a computation you should do. There's quite a few simplices here. So it's not hard, but it's somewhat involved to write it all down. Okay, right. So the reason I wanted to mention this example is once you do this example, you'll see that, and I guess I kind of remarked this before, in general, computing GKT, or determining what group it is tedious, and we will find a simpler way, which is called the Van Kampen theorem. And so that's where we're going to head next. And before we do that, I need to tell you a little bit more about free groups and free products. Okay, so this is a group theory topic. So let me start with free groups. This is just some algebra that we will need. So let's take S, a set, for example, so e.g. S could be a set with just two elements. And then we define the free group generated by S. So, I mean, this is the group who has generators S and no relations. So the elements are reduced words in S and inverses of elements of S, and also the identity. So for example, I guess actually my example is going to be S is ABC. So let me do that. So here is a reduced word Here's another one. Well, yeah. So you just write down words. So you just write down symbols in A, B, C, A inverse, B inverse, C inverse, and possibly E. Well, there are some rules. Like E is supposed to be the identity. So AE reduces to A. This word is just E. And similarly, like A, B to the 7th, B to the minus 7th, A, this inverse, this reduces to just E. Everything cancels and you're just left with the identity. And the operation is, the group operation is concatenate and reduce. So, I mean, when you multiply two things, you might not get a reduced word. So here you get AC squared C inverse B, and then there's a C that cancels here, and then you're left with ACB. Okay, so that's the product. Okay, so this is what a free group is. Now the next thing is free products. And maybe I'll just say that a free group, it's like a free abelian group, but it's not abelian. So I mean, note here that AB is not the same as BA. Okay. All right, fine. So free products is a generalization of this construction. So given groups G and H, the free product written G star H is the group well, I guess one way to say this is, let's say we have G is, we have some generating set with relations, and H has some other generating set with some other relations. Then the free product is the sort of smallest group that contains G and H, but doesn't have any further relations. So I mean, it has S and S prime generating sets, and then the relations of G and the relations of H, and nothing more. So for example, let me just give you an example. So yeah, I mean, elements in this group are words in the generators of G and the generators of H, and then you have to satisfy the relations that you know in G and H, but there are no further relations. I think it's easiest just to see, okay, so two examples. So Z star Z, this is, well, Z has a presentation like this, and so maybe we'll give the second one a new letter. And so you combine these and you just get the group with two generators and no relations, which is exactly the free group. The free group generated by two elements, as described on the last slide. Okay. Okay, a slightly more interesting example. Let's take G and H to both be Z mod 2Z. And so we have a presentation like this for G and similarly for H. And so the free product has this presentation, two generators, and the only relation is that A squared is 1 and B squared is 1. So now let's see what words look like in this, what elements in this group look like. So you can write like A. I mean, if you do, you know, well, let's see. If you're going to write down a reduced word, the only thing to follow this with is a B. You could either follow it with a B or a B inverse. I mean, B squared is 1, so B is B inverse. A is A inverse. And, well, right, so if I multiply an A here, I get back to the identity. So to get something interesting, I can multiply by a B, but I can't multiply by a B squared because that would just be A. And so then now I can multiply by A, and yeah, so the words just look like alternating, AB, and so on. Or you could start with B, A, and so on. So that's what elements here look like. To understand this group a little bit better, so here's an observation. So the subgroup generated by the word AB, so this is, so you have like, you have the identity element, you have AB, you have AB, and so on. And then you also have the inverse. The inverse of AB is B inverse A inverse, but B inverse is B and A inverse is A. So this is, so you also have BA, and then you have BA, and so on. So this is the subgroup. And the observation is that this subgroup is a normal subgroup. So it is normal in G. So that means if you conjugate by any element of G, then that sends the subgroup to itself. So that's easy to see because, well, to show this, you just need to conjugate by the generators. If it's true for the generators, then it's true for everything. And actually, you only need to conjugate, so by generators of G, and you only need to do this for the generator of the subgroup. And so it reduces to this computation. And here, what you see, okay, well, A inverse is A, and A squared is the identity. So this is BA, and similarly, this is also BA, which is still in the group. So that shows that this is a normal subgroup. And well, so then you can think about what the quotient is. So what are coset representatives? Well, we could work this out directly, but maybe let me give you a different way. So there is a homomorphism from G star H, G and H both cyclic group of order 2, to Z mod 2Z, defined by sending A to 1. So Z mod 2Z I'm thinking of as the group with elements 0 and 1, addition mod 2, and B also to 1. This is a homomorphism because the relations are satisfied. The only relations are that A squared is the identity, and A squared maps to 2, which is 0, and B squared is the same. Okay, so there's this homomorphism, phi, and the kernel of phi is words with an equal number with, yeah, it's just even words, even length words. But even length words is exactly this subgroup. Right? I mean, yeah, these are the only even words. I mean, according to how I've described how the words are, it's either AB, or BA, some number of times. So this means that our group, so this should have been G star H here. So then we conclude G star H mod this normal subgroup. This is isomorphic to Z mod 2Z. Well, oftentimes when you have a normal subgroup and a quotient, you sort of write it as in this way. So the subgroup generated by A and B, this is isomorphic to Z. So we have this Z subgroup and Z mod 2Z quotient. So what I'm writing here is what's sometimes called a short exact sequence. But this, you should just think of this as a shorthand that says that this group has a normal subgroup Z whose quotient by that normal subgroup is Z mod 2Z. So this normal subgroup was generated by AB. Right, but there's also a homomorphism back the other way, just by sending like 1 to A, for example. So what this says is that G star H has the structure of a semi-direct product, Z mod 2, like this. Okay, well, yeah. So I'm just trying to explain some of the structure of this in this special case, this free product of these two groups. Maybe this is something more familiar or maybe not, but this is a way to think about the group. And note it's not abelian. I mean, it's definitely not abelian. This isn't a product. This is not equal to Z times Z mod 2Z. Because here, you know, AB and A do not commute. One final remark about this group. It's actually a pretty interesting group. We've seen this group before. G star H is isomorphic to the subgroup of isometries of the real line. The group of isometries generated by the subgroup generated by two maps, A and B, where A sends X to minus X, that's an isometry, and B, I'm gonna write it here, sends X to minus X plus 1. Is also a nice isometry. And here notice that, right, so I have R and both of these maps preserve the integers. A is like doing a reflection about 0, and B is doing another reflection, a reflection about, let me write it here, a reflection about 1 or minus 1, or minus a half. So 1/2 goes to 1/2. So B is a reflection like this. And note that AB, so A and B both have order 2, and AB, well, what does this do? So first you do B, so this sends X to, so first you do the B and then you negate X. So that's X minus 1, I guess. Maybe let's do BA. Well, okay, whatever. If we do BA instead, then we get X goes to X plus 1. which is a translation. So this group that we get generated by these two elements, this is like the isometries of the real line that preserve the integer lattice, the integers subset. And so this you could think of as, so G star, well, so this group, which is isomorphic to G star H, is the infinite dihedral group. So you can think of this line with the integers inside as like a infinite-sided polygon, and the dihedral group is symmetries of a polygon. The symmetries of this infinite-sided polygon is this group generated by A and B, and that's isomorphic to this free product of groups. Okay, so this is a little bit of group theoretic background. Next week, we will use this, combine this with the Van Kampen theorem to do some fundamental group computations, more fundamental group computations. And we'll see that this is a better way in some sense than using this presentation given here.